It is September 4th. It's the TG3 meeting, and we have a couple of topics today. First, because we have special guests, Shane and Jesse Alma, we're going to start off talking about, and let me page back in the topic, decimal. We're going to start talking about decimal, and then if we have some time, we'll continue to recap our conversation about shared structs from the shared structs meeting last week. Um, may I invite Jesse or Shane to start the conversation?
Sure, I'd be happy to start the conversation. My understanding is that the topic of decimal came up last week. My colleague Nicolo informed me behind the scenes that it was discussed, and that my understanding is that Mark has been thinking about this a lot and shared some interesting insight there. And I would love if Mark, if you're willing to share some of what you've been thinking about, and then how this might impact the proposal, the decimal proposal that is, as it stands today.
Okay, yes, and considering that the last meeting was not recorded, it's especially valuable for me to try to recap that. As anybody who remembers the last discussion or have any of their own points to make, if I miss anything that seems relevant, please remind us. But I'll start off by recapping. So initially, there was the line being pursued for decimal was decimal as a new primitive type, very much in the same way that big int was added to the language as a new primitive type. And in that context, we agreed, for reasons that I'll come back to, that decimal as a primitive type would be, there's apparently a terminology issue between normalized and canonicalized, and I don't know what the difference is supposed to be. So I'll just say normalized unless somebody corrects me. Okay. And the issue with normalization, leaving aside nan and 0 versus -0, which are separate controversy, leaving those aside, the issue with normalization is that two decimal numbers of the same magnitude, i.e. that represent the same real number, have the same representation and are behaviorally identical. And I want to distinguish those two issues. I mean, it was the case that both of them were part of the constraint, but the reason I want to distinguish them is that JavaScript in most ways has a single numeric nan value, and all nans are behaviorally equivalent to all other nans, which is consistent with the idea that there's a single nan value. But we don't mandate a single bit representation of nan, and that becomes visible via typed arrays and array buffers. So the important constraint is that all decimal numbers of the same magnitude are behaviorally identical. And the reason why this was important for primitive decimal is that the magnitude comparison operators would apply to decimals, and those magnitude comparison operators are less than equal, greater than equal, and there's two equality operators, but the equality operators, when applied to something that can be compared with magnitude, are also taken to be magnitude comparison operators, at least double equal. And double equal and triple equal, there's an invariant between them currently in the language, which is that if type of A is the same as type of B, then A double equal B if and only if A triple equal B. And it's also the case that triple equal is only non-reflexive on NaN, and that means that aside from NaN, triple equal always gives. I'm sorry. Aside from NaN and 0 versus minus 0, triple equal always gives the same result as object.is. And there's a bunch of code out there that actually uses non-reflectivity to detect NaN, dating from before we added number.isNaN to the language, since the global isNaN predicate would do a coercion to number, which was very damaging. So in any case, there's all of these delicate invariants that all the primitive types obey, and object.is really must be, behavioral equivalent. I mean, if two things are not behaviorally equivalent, they must not be object.is. And so I think this really required decimals being magnitude comparable to preserve behavioral equivalence is the same as operator equal and equal and triple equal. Okay, then the browser makers, in particular, the makers of the high performance JIT browser engines, objected to adding decimal as a new primitive type to the language, not so much, if I understand it, not so much because of the complexity of a new primitive type, but because of the expected performance cost of a further overloading of the operators, that they didn't want to make the use of operators on existing types pay for the possibility that they're overloaded on new types. And I think that's that's a discussion we could have with them, because I'm actually a little bit skeptical that that's a necessary cost. But nevertheless, they did effectively veto that, and TC39 certainly has no enforcement powers, so all the browser makers have an effective veto, and anything that they will not implement is something that we must not standardize. So that put decimal in the realm of being a proposal for a new object type. And as a new object type, the proposal has not been proposing anything that could not be implemented as a library. So in particular, all of the magnitude comparison operations were all methods or functions that were no longer an attempt to overload these syntactic operators. And in that context, if decimal were forever only an object type, I waived my objection to non-canonicalization. Some people want to preserve the IEEE non-canonical form in which 1.00 and 1.0000 are distinct representations with distinct printing behaviors. Once you're not trying to overload the magnitude comparison operators and the equality operators, and not trying to repurpose object.is to be a magnitude comparison operator, because on objects it would just compare identity. Once you're not trying to do that anymore, having them be non-canonical doesn't violate any language invariant. And in fact, we can see that by the fact that library implementations of decimal as an object type, I don't know if they do, but they certainly can implement the IEEE non-canonical forms in a way that fully conforms to IEEE. So then the controversy arose when at the last plenary, it was raised that if we ever do have a decimal primitive type added to the language after the object type had been added to the language, that the relationship between the two could be retroactively rationalized by making the object type be the object wrapper form of the primitive type, in just the same way that there's a number object wrapper form and a string object wrapper form, etc. These object wrapper forms are usually useless, but they do exist in the language for the other primitive types. So if we added a decimal primitive type to the language later, it would be nice to be able to retroactively rationalize it this way. But at that point, the object form can't have any information in it other than what's in the primitive plus object identity. Right? The only thing the object form can add to the primitive form is the object identity. It would be very weird for the object form alone to have numeric information, if you want to call it that, that is not representable and preserved by the primitive form. So I made the statement that if we allow the object form to be observably non-canonical, and by observably I mean beyond just the bit representation as serialized through typed arrays, but the different printing behavior. If we allow it to be observably different, then we forever preclude the adding a primitive form later that is retroactively rationalized by having the object form be the object wrapper of the primitive. I think that says everything that was in my head.
That sounds really good. I really appreciate that you've thought through this. I really appreciate these. I've been taking notes the whole time here. This is really great stuff. That does also match my understanding of the conclusion that we reached at plenary, namely that if we were to do it with the non-canonical form, another way of referring to that is just to say like preserving trailing zeros or keeping all digits. There, I guess, different ways of thinking about that. Then
the other thing that came up in between you and I, which is worth repeating for the group, and that we actually did touch on in the group last time, was that the extra digits, the non-canonical, how many extra digits are kept in by the non-canonical form, how many trailing zeros are kept. There's the issue of how that propagates through arithmetic. And there's, and I remember when we were first examining IEEE decimal to be added to the language, and I was rather shocked to discover that it's not based on any mathematically coherent theory of representing precision or error bounds or anything like that. There are other numeric libraries that do a mathematically coherent propagation of things like error bounds, but that's not what IEEE does. What IEEE does is before people used computers for arithmetic, when accounting, financial accountants would calculate things, they ended up over time standardizing on a set of literally paper arithmetic practices about how much precision to keep. And then once sometime after that got standardized, it actually got written into, codified into formal accounting practice. And IEEE's precision propagation is based on that codification that started with paper arithmetic accounting practice. The other forms of error propagation that various numeric libraries do is there's interval arithmetic, and IEEE is actually was specified to help the so the hardware could help support interval arithmetic. You can so with interval arithmetic, you've got a lower bound and an upper bound, and when you do arithmetic in IEEE, you can set the rounding mode to round to lowest, round to highest, as well as round to even, which is the normal, the default. Obviously, you can't do that in JavaScript itself, but the reason why that's there in IEEE, among other things, is so that you could do interval arithmetic, where you, for example, add the lower bounds with round to lower, add the upper bounds with round to upper, and then the interval just keeps expanding to make sure that the numerically correct solution is always within the worst case interval. So that's one form of error propagation. The other form of error propagation is based on things like standard deviation and assuming random distributions, where you're not trying to get a worst case bound, you're trying to get a probabilistic bound under these statistical assumptions. And there are numerical method libraries that do that. None of that has anything to do with the error propagation that IEEE does.
I see Nicolo's hand.
Yeah. Thanks, Mark, for explaining like all of these and explaining like why we should not preserve trillion zeros. I think it would be good now if like maybe Jesse or I guess Shane could like explain the other point of view, that is why it's good to have trillion zeros, just to make sure they're all on the same page.
Sure. I would be happy to explain at least some of the motivation there. I think Shane could perhaps say more, but I can also offer some thinking, which is, as odd as it is with the IEEE 754 stuff, it does admittedly have some oddities, and these rules for preserving digits or propagating digits as we do, like fractional digits, I mean, as we do calculations, are indeed not easy to motivate and seem to be quite arbitrary. That's quite true. But I think the overall intuition that guides the preservation of the trailing zeros is along the lines of preserving all the information that is given to us. The idea being we don't know what source our data is coming from, and so that trailing zero, or just to be more neutral about it, all the digits that are given to us do contain some kind of information and presumably have some kind of content. And so IEEE 754 is, you might say, kind of conservative in that regard, by not just automatically killing or simplifying or canonicalizing things. And one of the use cases for a decimal, one of the primary use cases actually, is for a JavaScript engine to sit in the middle between two systems, where, for instance, a JS engine is communicating with a database, and we just get some data from there, and we don't want to make any assumptions about killing anything there, so we just pass it along. Or some other system, some kind of like a scale or something is telling us 1.0, and we conservatively say that, okay, that means 1.0, we'll preserve that, and the user can do with that what he pleases, or we just pass it along. And so it's a kind of conservative default, you might say. So that's the way I think about it. That's what keeps me happy
with the preserving trailing zeros. But there are some other more specific use cases. I think Shane could perhaps speak to those. Those are also kind of documented, I think, a bit in the proposal decimal repo to some extent. But I'd be happy if Shane, if you want to speak a little bit more to that, if you want.
Yeah, I can discuss a little bit about this. So, firstly, I just want to say that the motivations that I've raised regarding retaining the full precision of decimal values are largely motivated more by the ability of the data model to be able to represent values of varying precisions more than the exact behavior that IEEE introduces around the arithmetic of those values. When we discuss this topic, I often hear, arguments about, well, about the oddities of the way that IEEE handles the variable precisions during arithmetic, and how that's very, how that maybe is it's unexpected. Some of the ways that it handles those, but that doesn't really change the motivations around the ability to represent those trailing zeros. So I'll give a couple a couple specific examples here. The first is that numbers with varying precisions are actually different numbers. They're different numbers because the way you speak them is different. If you have 1 versus 1.0, if you have 5 versus 5.0, or for example, 2.5 versus 2.50, those are different numbers. You know they're different because I just spoke them to you in different ways. So those are different quantities. They're actually different quantities. They might represent the same point on the number line, sure. That's great, but they are actually different quantities.
And so when you say that, so when you say they're different quantities, I object to the word. I mean, I understand that they're different, but when you say, I would object to the word quantity in that sentence. They have the
But
same
also,
magnitude. They represent the same real number. So quantity seems like a
saying them in
confusing
different
terminology.
ways also doesn't inherently mean they're different. A dozen and 12 are still the same. 0 and nothing are still the same. Like, it's just because language has lots of ways to represent the same concepts often.
I mean, they're different. I don't know what word you'd like to use there. Different things, different nouns, different objects, but they are different. Even though they represent the same point on the number line. There are different ways of expressing that point on the number line, if you'd like it to be put that way. And the example that I very often use, that you've seen me use before, is the fact that when you're looking at, like, if you're looking at the rating of a restaurant in an app, you might see that it has 1.0 stars, and that's how you pluralize that string. Even though numerically you would use 1 star. It's a 1-star restaurant, but since it might be an average, it's 1.0 stars. It's 1.0 stars is the average of that, right? So that's the example I always use to sort of drive home the point that these really are different concepts. Whether or not they're they're different concepts to refer to the same point on the number line. So that's point one. Point two is that if we look at how other numeric libraries handle these in other languages, and in other languages, as well as other libraries you can find, like it's almost universally the case, and I've listed this out on the GitHub issue, on one of the GitHub issues, that most decimal libraries have the concept of precision in their decimals. Precision is I claim precision is inherent to decimal values, because decimal values are inherently a representation of a number in the base 10 system, and the base 10 system inherently has this concept, and contains this concept.
So would you make the same statement about base 2 numbers? Or, I mean, is there anything about this argument that's specific to the base of 10 as opposed to any other base?
I make this argument about the base of 10 because it's the way that humans represent numbers, and I think that representation of items in a base of 2, for example, is you could have precision values, and could represent that quantity, and I think it would be legitimate for a numeric type in the base of 2 to choose to represent numbers with precision, especially if it's relevant for retaining the accuracy and precision during numeric calculations. Um, the floating point of float 32, float 64, are often used in that context, and uh, right, and that's the example of a base 2 system, that a particular value in float 64 is typically understood to represent a range of values between a number that's one tick below it and the number that's one tick above it, and that's how it sort of chooses to represent precision. And that's just a little bit different than the way that decimal chooses to represent precision, because it doesn't have it's not based on the number of significant digits as much, right? It's actually it actually chooses to represent itself based on a string of decimal digits, essentially, a digit list. And the fact that like a decimal number is represented as a digit list is very fundamental in how internationalization libraries like ICU have handled decimals for years. And I think it's important, especially in the context of internationalization, to continue to think about decimals in that way. Okay, I'm done.
I have a question.
Go ahead.
Yeah. So you mentioned the example of like 1.0 star is like different from 1 star because it might represent an average. Is this like for this use case, is it important that precision is like carried out from the various operations, or is this something to attach the number at the end?
I'm not sure I understand your question.
Yeah, like for like cases like, for example, the reviews with stars, and you want to take the average. Do you think it's important in the case that the precision properly like carries through when like doing operations with numbers? So like when you sum all of them and then you divide by the number of reviews, for example, or is this just something that you would attach at the end? And like for this specific example, I already like asked you for an example and I saw it was at the end, but I wonder if it's in general something you only attach at the end or something that you need to properly propagate through.
Yeah, so I sort of touched on this at the beginning of my comment, but the way that IEEE handles the propagation of precision through arithmetic is of less concern to me. What's of more concern is the ability to represent numbers of varying precisions, and I think a very common a very common pattern that I see a lot is that when you're taking the average of several numbers, you will, perform your sum and your division, and then you will say, okay, and I would like this represented with, with 3 digits or 2 decimal places of precision, and that's sort of an operation that you would then perform at the end. Like you do your arithmetic, and then the last operation would be rounds to the nearest hundredth or tenth of a digit, for example. And like that's how I've seen this pattern fairly regularly. So and I think it's important that's how I would expect the precision to be propagated. And if IEEE propagates it in a different way during arithmetic, that's of less that's of less concern to me, if that makes sense.
So I think, first of all, I very strongly disagree with that. That's how humans think about numbers. Humans do not like $1 and $1.0 are exactly the same. And most people on the planet think of that as the same. And I just, the places in which the precision matters exist, but they're niche, like chemistry, physics, higher math. Like these things are important and the concept matters in these domains, but it's just not like a commonly understood concept. And like everyone that I like I was able to pick up this concept in high school classes relatively simply, but most people in those classes weren't, because it's not intuitive. And also the pattern you're describing of the numbers are their own thing, and then at the very end you tack in the precision information. That's right, that's how it's done, because you don't represent precision in the numbers. You represent precision separately, and you attach it to the number only at the point of displaying the information, when you no longer care about lossiness. And that's how not like capital N numbers work in JavaScript. That's like, you know, and as has been pointed out in the chat, right, like the importance of precision and how you handle that and stuff, like that is incredibly domain specific, and there just isn't a way to represent that universally. And so if there was a way to represent it that didn't detract from any other things, and that didn't disrupt the ability of all of these alternative representations to work, then that would be fine. But preserving precision in a JavaScript number system actively disrupts a lot of things, and I just don't think it has, like, I don't think it matches with most people's mental model, and I think it'll be really difficult to teach, explain, and so on. And as you said, you only care about the representation, which is fair, but people are going to be adding these things together, and unless we say all math just discards precision information, then like, and at that point, I'm not sure what the value is of preserving it versus just being able to attach it at the end. So I think we should stick with the precedent of, when you try to do a number to precision, you need it to be a string, because the number can't represent that.
Yeah, and I'll just elaborate on what Jordan just said, to say that the domains that Jordan mentioned, like, you know, chemistry and various other scientific domains where such things do matter, what matters there is a mathematically coherent notion of error bounds. And that has nothing to do with IEEE decimal.
I see Eli's hand.
Yeah, so for me, I was going to put a chat, but I'll just read it out. Oh, great. Closing the chat in mobile deletes it all. What was I going to say? I'll get back to it. I'll raise my hand when I'm ready.
All right, WebEx.
Okay, there. I got it. I actually had it on my clipboard. Perfect. Okay, so the issue, I think it's nice and it's more fundamentally pure to be adding mathematic and number features to a language from a language first perspective. And that is how almost all programming languages were designed. But it is currently 2024 and we have computers all over the world. They use various specific well-known number formats already. I think it's maybe advantageous for us to like potentially hook into any of those if available. I loosely know that like, or not, sorry, not hook in, but like to make it available such that it's easier for implementers to actually hook into it. I know that like IBM has some weird decimal internal format like on their Power 9 chips. And it's interesting to like think about what we have today and how to best use what we have. And this kind of goes into back to how Apple added that one instruction that literally is just for what was it, like number to string conversion or something for JavaScript, or what was it? These are all just like general vagaries of like how I feel like we might want to be like tackling the problem from the start, is like just considering available hardware and algorithms that we have already shipping.
I want to lift from chat that Nicolo. Oh, well, Nicolo's got a hand. I'll let Nicolo speak for himself. Go ahead, Nick.
Yeah, I was gonna say whatever's in chat, but like, I wonder if for the use cases of 1 and 1.0 convey different information, if for that we could have something like a number with precision wrapper that applies not only to decimal, it can also apply to floats. And so like in that object, we have a number with its precision. And when you compute something and then you want to pass it over to the next person, also telling them, look, the precision is this, you would like wrap it in that object. And
It's interesting. I wonder
assuming,
what the semantics. Sorry, go ahead.
and like assuming we will have one day in the future primitive decimals after that engines see that actually decimal are useful, like are used enough to justify the cost of having them as primitives, then that object is like as many objects as if we were just using decimal objects, just an object wrapped in some primitive numbers. And like maybe this also would have the advantage that precision is not limited to be like multiple powers of 10. You could have a number that's like with a precision of 0.5, for example. And also it's not just for decimal, you could also use it with floats, because I assume most code up there will keep using floats for a very long time, at least for as long as decimals are objects. So it would be great to have this possibility also with them.
Yeah, and I'm wondering whether that clears up the logjam for a primitive decimal being backed by a big D decimal prototype that is distinct from the precise decimal or precision with number. I see Jesse's and then Shane's hands.
I'm sure. I just wanted to riff a little bit on an idea that Mark was talking about earlier, and triple equals. I did a bit of digging about how triple equals would work if we were comparing decimals. And as you might imagine, okay, let me say, like at the bit level, can we, how complicated is equality checking? And when I say equality, I mean magnitude checking. And as you might imagine, if we are working in a world where values are always normalized, then checking equality is checking for quality of a sequence of bits. But if we allow these extra digits, then equality is a bit more complicated. And so you might imagine that this equality checking for a normalized version of this is actually pretty straightforward. But then equality for full IEEE is well, that's gets more complicated, right? It's kind of calling into a mildly elaborate function to check, are these things really the same magnitude? Just food for thought.
Shane?
Yeah. I don't. So, I'll just briefly. You know, I think that we have at least some understanding that that there is a difference between the concepts of 1 and 1.0. And again, my position is the fact that I just said those in different ways means that they're different things. Okay. But I'll go back to a point that Nicolo just raised, which is I think that if like I could totally envision a world where there is a decimal primitive type that worked on normalized values as well, in conjunction with with an object type that represents that is basically a wrapper around a primitive value with a precision attached to it, right? Something along those lines. Like I could totally see and would be happy with a future that was of that had that sort of shape to it. Because again, my position is I think that the ability to represent those two different things, which are things that do exist, is important. And I've given reasons why it's important. We can definitely debate about, how about, well, a lot of people, might think that they don't really see or understand the difference between these two things. And we can certainly have a debate for, I would certainly take the position that these actually are two different things, even to people who are not studying science in high school, that these actually are different concepts.
So in terms of they're different concepts because you say them differently, what about 1/3 or pi?
1/3 and pi, I don't understand your,
Well, so when we speak about numbers to each other in natural language, we say when I say 1/3, there's a particular number that I mean. When I say pi, there's a particular number that I mean. The there is no representation of either of those numbers in decimal, and I think you're quite sensibly not proposing that there be any such thing. But why doesn't that, the idea that number concepts that deserve their own utterance should have distinct representations? Why doesn't that argument apply equally well to 1/3 and pi?
I'm not, I don't really see how that connects with the idea of precision. 1/3 and pi are their own
No,
concept.
it's not not specifically precision. It's your more general argument that if the number concept has a distinct utterance, making it a distinct concept in terms of the way we speak to each other, then 1/3 and pi are distinct number concepts, neither of which is adequately represented by their decimal approximation.
I would agree with that statement. I would agree with that statement, and I'm trying to see how that connects to what I was saying about precision. I guess one could argue that the utterance 1.0 is like doesn't need to be represented by decimal.
That's
I
the
don't
point. That's the
understand.
point that I'm making. Is I'm doing a reductio argument, I suppose. I'm saying that if the distinction of the utterance 1.0 versus 1 needs to be represented because being a distinct utterance that we sometimes feel cause to say means that we should give it a distinct representation, then why does that apply to 1.0 versus 1 and it doesn't apply to 0.333333, et cetera, versus 1/3?
Yeah, I mean the answer for that is pretty simple. It's because the difference in utterance matters for the internationalization applications of it. And it's one of the, I often point to this as one of the top three issues that get raised, over time repeatedly to the ICU and Intel libraries about, number formatting and plural selection, basically behaving differently because of this difference. Um, uh, you know, um, and not both in Intel and in ICU and message formatting in general, right? Um, there's a lot of use cases for this. The use cases behind the formatting of pi versus 3.141, like those use cases could also exist. I'm not saying that they don't, but I'm saying that the use cases of having a difference between the utterance 1 versus 1.0 and how it affects the internationalization of strings and message formatting, which is something that that this group has agreed to be priorities and that we're definitely working toward as a group, like does matter and does come up a lot and does impact real life use cases. So that's why I would draw a distinction between one being more important to be represented than the other.
So as Chris points out in chat, we are at time, and some folks have, including me, have a subsequent meeting to run off to. I feel like we've just gotten started, and and propose that we carry this over to a future meeting, possibly even next week. And if we were to close with some words, I think that we are at a position where it's clear that this conversation must continue. Shane, it sounds to me like you're emphatically in favor of maintaining precision at the decimal level, and Mark and some of us also on the call agree that it's emphatically important not to have precision in decimal. We have also discussed one possible mitigation of that would break the triangulation between a decimal primitive and a precise decimal, or a decimal with precision, or a number with precision. Possibly even a protocol around precision that might be surfaceable in internationalization. In any case, let's continue our talk whenever it's convenient for everyone, or for all of the stakeholders.